Hi, I'm Ryan Patterson, a senior in aerospace engineering at the University of Michigan, and this summer I participated in the SURE program to get an idea about what graduate school or a career in research would be like. Through the SURE program, I worked with Professor James Forbes on the modeling of thin, flexible structures at sea in the context of a vibration control problem. These types of structures might include barges, ice floes, or even the novel concept of floating airports. The goal of this project was to design a controller that would minimize the flexible deformation of a floating structure due to wave forces. By approximating these structures as rectangular flexible plates and making assumptions about the behavior of the waves present in the surrounding sea, a mathematical model was formed, discretized, and simulated. Following previously published work, I simulated the dynamics of this fluid structure system and implemented several control schemes to suppress the induced motion of the structure due to the changing wave forces. Modern control theory relies on the ability to describe a system by a set of parameters, or states, which vary in time according to a set of differential equations. From this, an input-output model for the system is obtained, which maps disturbances to the resulting motion of the system. By using some of the information output by the system, the velocity of the plate's corners for example, a well-designed controller can determine the counteracting inputs necessary to restore the system to a desired state. An optimal controller is designed to minimize some objective that is related to the performance of the system. For example, a quadratic optimal regulator determines the optimal control input, U, which minimizes the performance index. The first term accounts for the energy of the system due to its motion, while the second term accounts for the energy expended by applying control forces to the system. Thus, the determination of the gain matrix K is such that a balance of energy removal from the system and energy expenditure by the controller is achieved. The state space model for the controller is then expressed in terms of this gain matrix. The controller's B matrix is obtained by solution of a Lyapunov equation for P. Here, QC is tuned until the desired performance of the system is achieved. With the state space model for the controller, it is readily implemented into the system for tuning. At the start of a simulation for this system, the states of the controller model, XC, are initialized to 0, as the controller does not yet have any information about the state of the plant. Disturbances from outside the system, waves from a rough sea for example, are included as part of the inputs to the plant system. The result of implementing this controller, providing forces only to the corners of the plate, is that the overall motion and total energy of vibration are less than that for the free response of the plate without the controller, making it a successful control system. I found working on a SURE project to be a rewarding experience, as I got to explore and work through a problem on a much deeper level, all the while getting to connect with my professor and his grad students in a collaborative setting. I highly recommend this program to any student at the U of M who is considering going on to grad school or who wants to make a contribution to Michigan's vast research community. Thank you.